Okay, thank you very much. So today I'm here to tell you something about molecules and star formation and galaxies, and I'm trying to combine all of these things in one single talk. So you will see, but before we start, there was already a quick introduction. Let me just say a few words about myself. So I'm coming from a medieval little town in the southern part of Germany, which is called Öhringen. You can try to pronounce it later. Then I moved, so in between I went to Japan, as was already said. But then for my studies, Bachelor, Master, PhD, I went to another medieval town in southern Germany, which is Heidelberg. It's a very beautiful historic part. And now I came to the not that historic, very modern urban Tokyo as a JSPS fellow to work here together with Nanase Harada. I also want to say quickly something about two of my main hobbies that I have, which are sort of reflected here. So I'm a really big fan of nature. So I really like going out there, going hiking, going to mountains. And I'm a really big fan of Japanese tea, specifically sencha. And combining these hobbies leads to mountain tea. So you go up a mountain, and then on top of a mountain, you have some beautiful tea. And these two left examples are from Germany, from two mountains. And the right one is Mount Otake, really close to Tokyo. And why I'm showing this, because this is sort of related to the talk. Because the tea is actually just hot water. But what makes the water so delicious is because in the tea, there's all different kinds of molecules. There's amino acids and catechins, and all of this what makes the tea taste so delicious. And in this talk, I will talk a lot about molecules, so these very, very small objects, and what they tell us about star formation in galaxies, which are those gigantic objects. But before we get started, let's first have a look into the basics, into what are galaxies. So I already know there's a couple of astronomers among us, so raise your hand if you're an astronomer. Okay, but not everyone, this is good. So let's quickly introduce galaxies. And I myself, so I'm an observing astronomer, I'm not a theorist. So what I would do to answer this question, what is a galaxy? I would have a look at an image of a galaxy. So let's have a look at the closest galaxy that we have, the closest galaxy to us. Nah? If it's not working anymore. And this is this image here. And you might have already guessed this, so the galaxy is this elongated feature here. This is the closest galaxy to us. This is our own galaxy, the Milky Way, so the galaxy that we are currently sitting in. And based on this image, we can already infer a little bit of details about what a galaxy is made of. So because we are sitting on a rock, which we call a planet, Earth is a planet, we have more planets in our solar system. If we look on the sky, we can also see that it's not working too well. There's a couple of stars in the sky, a lot of them on this elongated feature. So a galaxy also contains a lot of stars. And there's also, we see these dark spots in here, which are obscuring the view of what's behind there. And those are clouds of dust. So based on this image alone, we can already say a galaxy has planets, stars, and dust. And by only having a look at images like this, we could infer that our galaxy actually sort of looks like this. This is not an actual photo, this is just an illustration. What we are actually observing is something like this. But based on this, we gathered that this is roughly what our own galaxy looks like. So our galaxy is a rotating disk filled with a lot of stars, planets, dust, and there's also gas and dark matter. And this is, maybe, I'm not sure, did work earlier. Yeah, so we are sitting in this little circle here. We're sitting in the outer skirts of the galaxy. So this is where our Earth is located. Can you move it a bit forward? I'm not sure why it's not, doesn't seem. Okay, so I want to spend just a few minutes to talk about astronomical distances, because this is something that people often do not get right. So about the size of these objects. So the closest object to Earth is of course our moon. And there we talk about distances of about 1.3 light seconds. Which means if I want to send a signal from Earth to Moon with a big flashlight, it would take 1.3 seconds to reach the Moon. And if we want to put this in more physical aspects, I was really trying to visualize this because I like hiking. So if you take Mount Fuji and you stack it on top of each other, you would need 100,000 Mount Fujis to be able to go from Earth to the moon. So that's a lot of Mount Fujis. Maybe it helps visualize it, I'm not sure. But this is still just the closest object to us. So if we go a bit further, so of course we have not just our moon, there's more planets in our solar system, we have the sun, and all of this is still within this circle. It's so small we cannot even see it in here. So this is all just a tiny part in this galaxy. And in here we're talking about distances. The sun is about 8 light minutes away from us. So if we turn off the sun, it takes 8 minutes until we notice. Then we have the planets, the outer planets, we're talking about light hours. If we want to contact someone out here, it takes a few hours to contact them. And this was still just our solar system. The closest star to us, next to the sun, apart from the sun, is Proxima Centauri with about 4 light years away. So you need 4 years to send a message to this star. Next slide, please. And in comparison to that, our Milky Way, our galaxy, has a diameter of about 100,000 light years. So sending a signal across the galaxy, it takes 100,000 years. So this is really just, it's not just twice the size of a solar system, it's really a completely different order of magnitude. And I tried to visualize it, it does not work too well. It's about 10 to the power of 14 Mount Fuji stacked on top of each other. It doesn't help anymore, so at this point, it's just really impossible. But just to really try to give you an idea of how big these objects are. And this is also one of the reasons why we cannot take a photo of our Milky Way. We are sitting here in the outer parts of the galaxy. And to take a photo, we would need to send a satellite. It would travel for thousands of years to be far away enough to be able to take a photo. And then send a signal back, which takes another thousands, 10,000s of years, which is basically just impossible. So we're stuck on Earth, and all we can view is this elongated feature. Which is because we're sitting in the disk, we are looking edge on a disk which is creating this elongated band in the sky. And this is a problem, because if we want to study what's on the other side of our galaxy, we have to look through all of that material that's in the way. We just have this image, and there's a lot going on with Gaia and beautiful science that has been done, but it's still just very difficult to gain an idea because you always have to look through all of this. But luckily, our galaxy is a thin disk. And we cannot look through the disk, but we can look up and down. And if we do that, we see that there's more galaxies. The next galaxy, apart from the Milky Way, is the Andromeda galaxy. And we're talking, this is the closest galaxy, 2.5 million light years. So the closest galaxy to us. And this is also not the only galaxy, there's more galaxies out there. This is one of the first images taken with the James Webb Space Telescope. And this shows a field in the sky. If you take a pinhead at 1 arm's length, this tiny part in the sky is what you're seeing here. And everything that looks like a Christmas star is actually a star in the foreground. But then you see there's multiple objects here, which are all galaxies. There's hundreds of galaxies in this single part in the sky that we see here. And this is a fact that's actually that we only know since about 100 years. So about 100 years ago, this was very controversial. In 1902, so a bit more than 100 years ago, people had images like this one, observations of Andromeda nebulae. So what is now Andromeda nebulae? I thought we were talking about galaxies. Well, back at the time, this is exactly what people were discussing. In 1920, there was the so-called Great Debate, a discussion between Harlow Shapley and Heber Curtis discussing what the origin of these nebulae is. Could it be that those are just similar to our Milky Way, and the Milky Way is just one out of many galaxies? Or is everything just part of one gigantic Milky Way? So these nebulae being in the outskirts, and it's all, they didn't know the size of the Milky Way. And of course, I did already spoiler you. We know there are other galaxies out there. The Milky Way is just one out of many, many galaxies out there. So again, this is just one teeny tiny field of view in the sky. You can do this in any direction, you will see a similar picture. Thousands of galaxies, each of them filled with millions of stars and probably the same amount of exoplanets. So there's a lot out there to study. And you can all see, these galaxies, they all look a bit different. Some of them are a bit more redder, a bit bluer. Some even have a bit of structure in them. So let's talk quickly about different kinds of galaxies that exist. We do have elliptical galaxies, gigantic collections of stars, which just look elliptical. We also have spiral galaxies, like our Milky Way, disk galaxies that are rotating. And we see it looks like a whirlpool. We see the swirls in a whirlpool. Those are the spiral arms. And these galaxies, they can also be interacting with other galaxies. They can merge, they can fly by each other. So several things can happen here. We also have galaxies with a bar, where you have spiral arms, and then suddenly they change their direction. And this thing in the center, this is a bar, which about 2/3 of galaxies seem to have. And we can have different kinds of rings, really big rings, but also smaller rings in the centers of galaxies. And the interesting thing is, if we now have a look at the distribution of stars in those galaxies, then we see it's not the same everywhere. Specifically, if we have a look at young stars, where are the young, the hot and energetic stars? Where are they located in the galaxies? And we see that those young stars are specifically on spiral arms, on rings, but they're not on the bars, and they're not in elliptical galaxies. So it seems that these structures, they do not just look beautiful, but they are actually connected with the star formation. They change where star formation in the galaxy seems to happen. But why is this the case? This is exactly what I'm studying and trying to understand. And to do this, to dig a bit more into the science here, let's have a quick look into the theory of star formation. And I'm trying something here. Who knows what this is? Some nodding. I hope you played with this as a child. Very fun. So bricks, it can be made from Lego or other companies. Let's just for a second assume this is sort of the material to build a star. And what we need to do to form a star is we now need to compress this. And if we do this, we will automatically start to stack bricks on top of each other, building more and more complex brick structures. And we can do this even more. We can compress it more. We stack more and more bricks on top of each other. And if we continue this even more, at one point, we have formed a star. They're Star Wars fans, great, okay. Of course, this is very simplified, but more or less something like this is happening. And you could imagine now these bricks being different kinds of atoms. And what happens if in the formation of a star, you get to denser and denser regions and molecules will form by just stacking these atoms on top of each other. And here's now a bit more scientific view of this. So star formation starts with a cloud of dust and gas, in which we have our bricks, we have our atoms. If the conditions are right, parts of this cloud will be able to collapse. So the gas gets compressed, we get denser and denser regions, higher densities, we get molecules in there as well. And if at one point the conditions are so extreme that we will form a protostar. So what happens is we get higher and higher densities, and at one point we reach the point of nuclear fusion. And this is really crazy, because now we take two bricks and we form a completely new brick. So this is really mind-blowing, in my opinion. And this is exactly what our star thinks as well. This is so mind-blowing that our star blows away the cloud it was initially born in, and we are left with the older star and the disk of debris surrounding it where planets can form. So this is roughly the formation of stars, and we can actually see this in the background. This is an image with the James Webb Space Telescope of the Carina Nebulae, a few thousand light years away from us, so very close by. And you can see the orange, so the colors have not really any meaning because it's infrared observations. But you can see this orange thing, this is a cloud. It's a bit hard to see any denser regions in here, but if you look in these regions, something is blowing holes into the cloud. Something is rupturing, there's like holes appearing in here. These are new stars that blow away the cloud that they have been born in. So this is the process of star formation we see here. And the old stars, they're up here. They've already destroyed or pushed away the cloud they have been born in, and the old stars are here, and the cloud where new stars form is down here. So we can actually see this here. But this is also not the end of the story. So this is how we form a star. But the stars, they don't live forever. Our sun is currently at a midlife crisis. And there's other stars that don't live as long, so they already did something really spectacular. They sort of blew apart. At the end of the life of a very massive star, this can happen. So a star that basically ran out of fuel, blew away its outer envelopes, and then in the center we are left with a neutron star which illuminates this thing. And this does not only look really beautiful, this is the Crab Nebulae, also a few thousand light years away. But this material that gets ejected is not lost. This material can be used again and can end up in the next generation of clouds, in the next generation of star formation. So it's a really big recycling process. So if anyone tells you you're made of stardust, it's sort of true, but you could say the modern version, we recycle stars. I think that sounds way cooler. And the nice part is here also that in this recycling process, we already saw, like, in these stars is where new bricks and new elements are formed. And these, what happens with them, of course, they end up in the clouds, and they also end up in the denser parts. And this is basically the material that we need to form our molecules. So I'm really interested in understanding where will the next stars form. So I want to understand where the molecules are, because they really tell us sort of like this connection, this step in between here. Okay. So we already saw, like, galaxies are really cool and stars do not form everywhere the same rate. To understand this, we wanted to look into clouds, because in the clouds, this is where the stars form. And how do we find the dense regions in those clouds? By using molecules. But how do we do this? There's already the question earlier, it's not infrared. Someone asked this already. So how do we observe molecules? Well, let's ask it a bit the opposite way, because we're not observing a single molecule. This is something people often think, like we're really having an image of a molecule. This is not what we're doing. Instead, molecules emit light, and we are collecting this light. And if then a region is really bright, it tells us there's a lot of molecules, basically. And I apologize for this slide. I had a lot of fun doing it. So how to visualize this really, really easily. So let's say we have our little molecule here. The first thing we need to do is we need to excite this molecule. How we do this? By giving it some energy. And how exactly we do this? So either we give it a photon, or what happens really frequently, you bump into another molecule, your party friend. You all know this one person that likes to party really hard. So you bump into this party friend, and they have good vibes, they want to party. So what will you do? You will party. So you go to the dance floor. The molecule is really, it wiggles around, it spins around on the dance floor. Molecule is excited. Well, until it is no longer excited. Spontaneous de-excitation, and our molecule emits a photon in a very specific frequency, which we can then observe. This is a bit more the scientific view of this. So molecules have different transitions. They can, if they're excited, they can change sort of their energy states, and this is what, how they can send out a photon. And this can happen at different frequencies. What I'm mostly interested in is the molecular rotations, because they happen in the cold interstellar medium. So in galaxies, the conditions are usually not that extreme. It's very cold. So there's not that much energy available. So you just need a little bit of energy, which is just enough to give them some different states of rotation. So this is exactly what we can observe. Which means, as you can see here, sort of in this image, this happens at very, very long wavelengths. So we're looking at sub-millimeter, millimeter, some even longer wavelengths. Okay, so how do you observe this? Let's quickly talk about radio telescopes. So all of this is usually considered part of being radio astronomy. Here you can see the Atacama large millimeter and sub-millimeter array, observing millimeter, sub-millimeter frequencies, wavelengths. This is in the Chilean, in Chile, top of a mountain plateau. And what we just already heard is about the wavelengths. Because for observing, there's one simple thing we need to consider. The resolution depends as the wavelength divided by the size of the dish. So if we have a really long wavelength, which we have in our radio millimeter observations, we need to build a really, really large dish size so that we have sharp images. And this is a problem because at one point the dishes are so big and heavy, it's very hard to stabilize them, to get them moving. So this is really tricky. What you can do instead in radio is you take multiple telescopes, they observe a target simultaneously. In projection, it appears as if it would be a very, very large dish. And this is what you can see in the background here as well. So this is sort of like how you connect these telescopes. Yeah, well, you might think, okay, there's someone staring in the night sky all day long, this is boring. No, let me tell you about my experience. I was observing at the IRAM 30-meter telescope. So this is a telescope, it's this here, in southern Spain in the Sierra Nevada, Pico Veleta, so about here. And it's a 30-meter diameter dish. So this is now just one telescope, but it later will be combined with other telescope observations as well. So it's also part of some of the observations I'm showing. And those are all my photos, by the way, so I'm not making this up, what I'm showing. So yeah, there's also other telescopes in here, but yeah, this one is the 30-meter telescope. So in the telescope, in the top part, you can visit this if you're an astronomer. There's all the technical part. This whole antenna can move, so you have motors, you have cables, you have receivers to do the observations. You can even go in there while observations are running. It's moving very, very slow, so that's no problem. You just need to turn your phone off, otherwise all the observations will be destroyed. Hopefully I did that, I'm not sure. But this is not the only fun part. So observing, of course, the technical part, but in the foot of the telescope, there's actually a gym. I'm not making this up. So actually, in this garage, in the foot, you can go and you can go pumping. There's a lot of weights, so if you're bored, this is what you can do. And you don't even have to step outside, because this telescope, there's an underground tunnel connecting this telescope with the main building, which is here. Because you don't have to stay in the telescope, so this is up the mountain. You usually stay there for about 1 week, which is also what I did. So you're sleeping in there, you're doing everything in there. You're also doing the observations from there. There's the control room. This is how it looks like out of an old James Bond movie. It's probably as old, but it's still working fine. So you're sitting behind these windows, and then you can press some buttons, and then you see this gigantic telescope. You can see it slowly moving. Once you press a button, this is really cool. Yeah, so there's an operator who knows all the technical stuff on this side, and I'm sitting there with 4 monitors feeling really, I'm so professional, but actually you're just clicking the same 5 buttons over and over again and hoping to not destroy anything. But this, of course, you have to spend there 1 week, and yes, you can go to the gym, but they also need to give you really good food. It's southern Spain. This is jamon, this is like this size meat, and you get a knife, you can cut it yourself. They also have a lot of wine, so you can have a lot of fun while observing. And this is also not enough, because of course, yeah, you can go to the gym, but maybe in winter you want to do something else. Right next to the telescope, there's actually a ski resort. So there's the ski lift that goes down on the other side of the mountain, so there's a ski resort. When I was visiting, as you can see, there's not enough snow, unfortunately. So those are all photos. I'm not making this up. Yeah. So I couldn't go skiing, so instead, what did I do? Of course, I went hiking and then had some tea on top of a mountain, which was really nice. So yeah, this is how fun observing can be. So if you ever get the chance, this is IRAM 30 meter. You can even, if you just want to go skiing, you can pass by in winter and have a look at the telescope, which is a pretty nice experience. But now let's go to the actual science. Let's have a look at how the images look like. So this is now one example. This is not with the IRAM, this is with the ALMA telescopes. This is one example of molecular gas in a galaxy. This is carbon monoxide, molecule we also have on Earth, very toxic. And this is the rotation transition 2 to 1, just the different states of rotation and how they change. This is one galaxy, and we can also have a look at the same galaxy in different wavelengths observed by different telescopes. So we're basically looking at different colors, different wavelengths. So very right one, James Webb Telescope, infrared observations, ALMA molecular gas, AstroSat ultraviolet observations, very, very energetic observations, and the Hubble Space Telescope giving us basically the view of what our eyes would see, the visible range. And all of this gives us insights into the process of star formation. So James Webb shows us where the dust is, where the clouds are located. Molecular gas sort of in those clouds. The UV showing us those freshly formed stars. And Hubble giving us just a sense of the overall distribution of stars. So by using all of these different telescopes, we can learn a lot about the cycle. And I'm, of course, most interested in the molecular gas. So let's have a closer look at those. We can, of course, not just do this for one galaxy, but do it for more galaxies. This is from the so-called FANG survey. It's a collaboration that also some people here are part of. And those are all observations of carbon monoxide. And we're seeing 100 typical nearby galaxies that are all actively star forming. So they're very similar to our Milky Way. Just there's so many out there, very, very similar. Milky Way is a fairly normal galaxy that forms stars. And what we see in here, we color-coded by structures. On the left side, if we see a bar or no bar. And on the right side, if we see different types of spiral arms, if it's 2 or more, or arm segments. And why is this important? Because this already tells us something. So the galaxy structure is visible in the molecular gas. And if we turn this around, the molecular gas is responding to the structure. It's sticking to the galaxy's potential. It's following those structures. And this is really important to understand what's happening there. So let's dive into what molecules tell us about star formation in those galaxies. So if we have a look at the galaxy, let's have a look first. Here I masked the spiral arms. And here's now an example of the CO observations. And I put a mask on so you cannot see it too much. But it's very bright on the spiral arms, which means there's a lot of emission and a lot of photons coming from molecules. There are probably a lot of molecules there. So a lot of molecular gas. And what happens here? We have a little cloud sitting on a spiral arm. Now cloud happily forms stars. So this is great, because that's something that we can learn. If there's a lot of dense gas, there's also a lot of star formation happening. We can do the same, removing the spiral arms, excluding everything, the spiral arms in the center. And what we see is, of course, it's less bright. There's less molecular gas, less star formation happening. Seems, like a bit stupid, like a very, very simple law. But this is actually already the first law of star formation, the so-called Kanji-Schmidt relation. This is sort of now the expert slide with a bit more scientific background. So if we compare star formation rate in a galaxy versus molecular gas mass, there's a really beautiful correlation here. So basically telling us more gas, more star formation. And this is now from a recent paper from 2023, but this goes back to 1959 and 1998, the work of Schmidt and Kanji. So this is already like a really fundamental law that we have in astronomy. But, there's always a but. We can have a look at the bars. 2/3 of all galaxies seem to have such a feature. So this is sort of the bar feature. You have spiral arms and they suddenly change their direction to go to the center. And here we see it's quite bright. There's actually a lot of emission from those molecules. There seems to be a lot of molecular gas. But what our cloud is doing, those are sort of the orbits that are in the center. Our cloud is not feeling well. Our cloud does not want to form stars here. We have plenty of gas, but no star formation happening. So it does not follow this Kanji-Schmidt relation. So what's going on here? We think, because those bars are sort of like a Autobahn, like the highway, German highway. So what does this mean? So basically we think that the gas is really, really rapidly transported to the center. So it's being funneled to the center. And there's sort of no time for star formation. There's a lot of shear ongoing, a lot of pressure, and that's preventing the cloud from forming stars. And here's again sort of an expert slide. We can actually have a look at the dynamics at a velocity field of a galaxy. So here's sort of a velocity field, red just meaning something moves away from us, blue it moves towards us. And this is just what happens if you have a rotating disk. So you have a disk, you're not looking on it face on, it's sort of like a bit inclined, and some part is moving towards you while some part is moving away from you. And this produces this beautiful pattern here. And we can model this exactly like just a rotating disk. And we can subtract this model, and you can see that specifically in the central part, there's a lot of residual velocity. So the gas in the center is not just rotating, but instead it's being funneled to the center. It's really rapidly streaming there. Okay, but what happens next? So the gas is being transported rapidly to the center. It doesn't just get swallowed by a black hole. We cannot even see it in here. That's way too small. Before anything happens, it accumulates in central rings. These are just the little zoom-ins into galaxies. You can see these rings forming here. And these rings are really bright, and a student of mine, Damien Gleis, analyzed these in more detail and finds that these rings are 2 times more efficient in forming stars than what you see in the outer skirts of the galaxy. So here we have the opposite problem. We have plenty of dense gas, and we have too much star formation. It also doesn't follow this Kaneke-Schmidt relation. So it doesn't work everywhere. We see there's a couple of outliers. But there's also one thing that I haven't really told you yet. So let's talk about this quickly. There's different kinds of molecules, and these different kinds of molecules trace different things. Early on, I was introducing sort of these bricks as atoms. We have molecules, the density increases until we at one point get a star. And in this process, we have the molecules forming in more complex molecules. But there's actually a second path what can happen. We can have molecules, but then the gas disperses again. The density decreases again. We can have molecules, and suddenly we have atoms again. No star is formed. So depending on which molecule we are looking at, this might not actually tell us that in the end, there will be a star. And on top of that, there's also chemistry. You're trying to do chemistry on scales of galaxies. Something that, I'm also trying to do right now at NAOJ, because there's a lot of experts. But you can have molecules reacting with each other, forming different molecules. So you not only just having a molecule does not necessarily tell you that there will 100% be a star. And what can you do? Just to understand this better, more molecules, more different kinds of molecules. This is now the central part of the so-called Whirlpool galaxy. And those are observations of all different kinds of molecules. And let's zoom in a little bit. So we have isocyanide, we have diazenylium, isotopal logs of CO. But what you can see immediately, the center. In here, the center looks completely different in some of these molecules. And we think the reason for that, so now we can sort of try to do chemistry, is because in the center there's an active galactic nucleus and a jet that's sort of pushing out some of the gas. It's basically blowing a hole in our gas disk. And this is what we're seeing here. And some of the molecules are more robust than others, some are sort of still surviving in here. I'm going to skip this due to time reasons. But basically what you can also do is you can do a comparison between just taking the ratio of different molecules in comparison. And you can see that indeed, just looking at different colors, you see the center is always off. Something is really weird in the center. And I tried to understand this physically. So what we did is we had a look. So this is again sort of the expert slide, skimming in a bit of actual science here. We had a look at pressure terms, the pressures that are acting on the gas. And just looking at the colors, you can see again, the center indeed is off. So perhaps this is one of the reasons what's driving these differences here, that there's different pressures acting in the center. One more thing that I now want to answer, the last thing. This whole talk was about if we can predict where future stars will form. So can we actually do this? And there's one molecule which is specifically good at thriving in very, very dense regions, which is diazenylium. So probably in all of these regions, this is where future stars maybe will happen. And we spotted that there's one specific region which is really, really bright. So why is it so bright? We got curious. And we had a look at another molecule, which is a tracer of telling us where shocks are happening, so things colliding really rapidly. And this is also really bright in this region. But why is there a shock happening? So we were asking even further. And then we had a look at the dynamics again. So this is now torques, it's the forces acting on the gas. And it's just a hypothesis that here we have sort of opposing forces acting on the gas. So perhaps there's large streaming motions, gas is being funneled to this position, which is causing, so we have a crash of gas flows causing a shock, and the shock is then causing dense gas to form. This is what we think might happen, and this just shows how important it is to have a look at these large-scale structures, because it's all connected with the process of star formation. With this, I hope I could tell you something about what molecules teach us about star formation. Galaxies, there's plenty of galaxies out there. Our Milky Way is just one out of many galaxies in our universe. And our sun is also sitting in there, is one out of many stars that once was able to form. In those galaxies, we have molecular clouds, which are one really important step of the formation and the recycling of stars. So understanding star formation, we want to have a look at these dense regions in the clouds, which are the sites where future star formation might happen. And to trace these dense regions, we made use of the fact that we can have molecules in there that form. So molecules telling us where the dense regions are. But there are different kinds of molecules. And different molecules can tell us different conditions, different physical conditions in the gas. And then having a look at a galaxy as a whole. In the spiral arms, it seems that there's very simple star formation laws. More gas, more star formation. Outside of the spiral arm, less gas, less star formation. But then we also had a look at the bars, where this law does not apply anymore. A lot of gas, less star formation happening. And also the centers of the galaxy, which is very chaotic if there's an AGN and there's a lot of pressure and we don't really fully understand what's going on in there. And having all of this in mind, if we go back to this image of the Milky Way and our location in here, maybe, just maybe, take this with a grain of salt, maybe it's no surprise that we are not sitting in the bar or in the chaotic center of the galaxy, but we are sitting out here where there's very normal laws of star formation. And if there's one thing you should take away from this talk, molecules are super cool. They make your tea taste nice. They make us find star formation. So thank you very much.
Cool. Thank you, Sophia. So we have time for question and answer. So please raise your hand and I will call on you. And please wait for the microphone from Stephen. So yeah, we'll open the floor for questions. Yeah.
Good evening. Thank you very much for your talk. I've recently saw on a museum, I recently learned about this thing called the chirality of a molecule at museum. And you got the left side and the right-hand side of the molecule. Does that also affect the star formation? For example, the N2H plus on the left side, if you have more of them, you have more star formation, or is there any connection between that chirality and the star formation?
So, I mean, we're not able to view the actual molecules. So I don't think we're able to distinguish between the chirality of those. So we are far from getting into this level of detail. So right now it's all about just detecting if there is this sort of kind of molecule at all. So I would say this is not yet any concern. Maybe at one point if we get really good at the observations, but right now this is, so it's more about detecting the molecule in the first place. Because specifically this diazonylium is really, really faint. It's sitting in really small regions, really dense cores in those clouds, which makes it very faint if we want to observe this in galaxies. So this was actually one of the first times we get such a big view of this molecule. So we are far from getting into these details. Maybe in the future.
All right, thank you very much.
Back there.
Hey, thanks for the talk. Not an astronomer, so maybe stupid question. So my understanding is that planets form in a very similar way with a cloud of dust that aggregates to form some denser objects. Could there be clouds in galaxies that would create planets instead of stars?
I mean, there's probably experts on planet formation here as well, so probably I'm just saying something wrong. But usually you form your planets in this sort of in the same process. In a process where you form a star, you more or less automatically also form your planets. I'm not sure if there's ever a case of planets forming without a star. I think planets can then migrate, go somewhere else, but usually they form in the debris of a star forming. So in this process, your cloud, and then in the cloud, I mean, it's very, very small regions in there that collapse and form a star. And then sort of these remnants will form a disk of debris around the star. And this is where you get your planets. So it's connected with each other. I think you never get a planet without a star. but there's maybe an expert. No.
If the cloud is not dense enough to concentrate until you reach ignition, maybe you could have a brown dwarf or
Yes.
form a simile gas giant being formed.
Yes, yes. I'm not exactly sure what the transition is between then a star and a planet, but of course it happens. But I was more thinking about the rocky planets. Can you get? Wait, you're doing exoplanets, no?
Thank you.
Right there.
Thank you for your presentations. It's quite interesting. Especially quite interested in the reaction part. So if you have this data from different molecules, if you kind of superpose it with each other, you can kind of statistically simulate what will happen. And so that's kind of cool as well. And my question is, you only show like 6 or so molecules, but well, in theory, you can have like different weird molecules, especially with, I don't know, out there, who knows what happens in terms of reactions. So is there any reasons? Is there any like reasons why we're limited into that kind of like observations at the current moment?
Yes. So with other instruments, you can get more different kinds of molecules. So in your instrument, you usually need to limit a certain frequency or wavelength range. So you only get the molecules that emit in this range. And you can do multiple observations, you get more and more molecules. So this was basically one observation, what I'm showing in the end was from the ERAM, like observed at once. You can add more frequencies to that, more molecule emissions. Why we chose those? Because those are the brightest. Why are those the brightest? Because the most common. Most of these molecules I was showing, like HCN, so carbon, nitrogen, those are the most common most common atoms that are formed in our stars. So if you want to have more complex molecules, you also need to have the elements to form them. Everything with carbon, hydrogen, nitrogen, those will just be the most common one, and therefore the brightest one, the easiest to observe. And the more complex one, if they're just less abundant, means they're fainter.
It's harder to
Much, much harder to observe. So we're always trying, of course, to get more molecules. I think there's about 200 something that are detected on Earth we have many more molecules, but in space there's about 200 different kinds of molecules detected.
Cool.
Yeah.
Cool. Thank you.
One question, do population of stars, so population 1, 2, 3, would the difference of population star interact with your study? So I mean the level of metallicity, depending on the level of metallicity, the reaction, I would say, would be with different molecules.
So in Jein, which is a German word for yes and no, Jein, the atoms or molecules that are in the star, of course, they are locked. Like we're not observing the stuff that is in a star, because that's part of the star. But of course, if there's more evolution, so if there has been the longer you wait, the more elements you get, so the metallicity will increase. So it will also increase in your molecular gas. But because the disks are rotating in those nearby disk galaxies, you have very efficient mixing process. So you specifically, we were looking at the central part. You expect it to be quite well mixed, so you wouldn't expect any difference. Because the time scales at which stars form and get destroyed is still long enough that in comparison, that it shouldn't matter. But let's see.
Okay, so only very, very redshifted galaxies could have a different behavior. So
yeah, but it
it's
depends
irrelevant.
If you still look within a galaxy, there's very efficient mixing. So then you have an entire galaxy that has less elements. This is what is observed. Yes, the metallicity. So how many different kinds of elements you have changes with redshift in those galaxies, and so also the molecules that you see changes with redshift. That's
Over there.
Thank you so much for your presentation. You mentioned observing how the stars are being, like these different environments that make it possible for stars to form. and then you mentioned chemistry, and looking at like your theories or how things based on these conditions something can happen. Is there space, or there's some things we just can't really explain that it might even suggest that new elements might be found, or things are pretty much like if you say these are like the elements that create this particular that creates stars, but is there something that where you're like, hey, this is not behaving the way that I would expect, but maybe there's something else that can happen?
So you mean, for example, if we get too much of one element, could there be a new process creating elements that we haven't understood yet? Well, I think so I'm looking at the molecules, which is already like atoms connected with each other. The problem is that the chemistry, so the molecules just reacting with each other, is incredibly complex, and trying to model this, so Nanase is doing this, we cannot just go there and measure what the conditions are, what is the temperature, for example, which changes the reactions. And then also you don't know what other elements and stuff you have. So there's just so much uncertainty that we wouldn't really be able to measure this right now. So just really trying to model different reactions is already quite a complex thing to do. So I don't think we also would be able to measure this at the moment. So we're still trying to figure out just the molecule reactions, what is happening there. Again, we're trying to do a chemistry on galaxy scale. So we're not really in a lab where you have a tiny bit, but it's more a statistical view. But it's a good point, definitely.
Maybe time for one more question right here.
Thanks. So you talk about all of these observations being in the present tense, but actually what you're looking at is in the past tense by several 100,000 or millions of years. So is there ever any wonder or prediction, simulation of how a galaxy would look today versus how it looks at the moment via light years of observation?
That's a very good question. I'm not aware of any simulations that try to take these galaxies and push these into like the Milky Way present. But on the other hand, even if it's so those galaxies are a few million light years away, the processes that happen in there, and also the star formation, happens very slowly. So I don't think it would be that far off. So those are the nearby. Of course, if you go to higher redshift, you see a completely different picture. But we don't know how it evolves to the present, so I guess it would be difficult to model, to make a simulation. And the processes are slow, so it should not change your view completely. Like, it shouldn't be that suddenly you have, completely new things happening in the galaxies. It will still follow the same rules and just maybe slightly higher metallicity in the end. So that's not really being done. So usually you just take the Milky Way as it is and compare it to nearby galaxies. And usually it matches quite well. So yeah, those changes should be small enough that we don't really see them at the moment.
Okay. Thank you.
But yeah, again, those are the nearby galaxies. Further away galaxies is, we have cosmology experts here, so this is a different picture.
Okay, so I think that's all the time we have for questions. So let's thank Sophia again.
Thank you very much.
How do I